Hi, this video deals with the introduction to the science that studies our planet, its materials, processes, and all the events that resulted in everything we see around us. This video is a brief summary of the most important aspects of geology as a science. We review significant events during its development as a science, some of its contributors, and founding fathers. We explore some fundamental concepts, doctrines, and its historical development to realize that it is still an ongoing and evolving dynamic science, with many avenues to explore and to be amazed about. I particularly love it, and I want to share with you that passion. My ultimate goal in doing this is that if we understand how our planet works, we can appreciate even more the miracle of calling it home. Enjoy it, and don't forget to like, share, and subscribe. This channel is dedicated to the understanding of our planet, its processes, products, and its history. The science that studies all these aspects is called geology. My main objective is to cultivate the amazement and passion that I have for geology in an attempt to share with you that awe-inspiring feeling. Naturally, while doing this, I will be sharing with you different videos that will deal with several aspects of geology as a science. I hope that you find this channel and its content very inspiring, and that throughout this journey, you can also learn. But more importantly, that all of you cultivate the admiration for our planet and for the way we understand it. The Earth is a unique place, quite special, full of wonders, still enigmatic in many aspects, and so far, the only thing that we all have in common, the only place that all of us can call home. Our modern approach to geology conceives our planet as an ongoing and evolving entity, a constantly changing dynamic systems with many parts that interact with each other, resulting in a complex history. Geology is the science of the earth. The term geology comes from the Greek geo, that means earth, and logos, that means discourse or treatise. Thus, geology deals with the study of the earth. As a modern science, geology is subdivided into two broad areas: physical geology and historical geology. Physical geology deals with the materials that compose the earth and aims to understand the many processes that take place internally and externally. This is beneath and upon its surface. Historical geology deals with the origin of the earth and its evolution through time. It strives to establish an orderly chronological arrangement of the multitude of physical and biological changes that have occurred in the geological past. Commonly, physical geology precedes the study of the earth's history because we must first understand how it works, all its systems, processes, and products before we attempt to understand and organize the events that have occurred in its history. Like many other modern sciences, geology is subdivided into many areas and seeks for the support from other sciences. That also means that both physical and historical geology are further divided into many areas of specialization with their own concepts and analytical techniques that makes up for a comprehensive study of the Earth's materials, processes, products, and its history. However, as any other science, geology has undergone its own path into the modern science that it is today. The reason for this is that geology indeed affects our lives, also due to the inherent human nature whereby we are curious creatures, always attempting to make sense of what is around us, including all the processes we can perceive through our senses. The nature of the Earth's materials and processes have been a focus of study for centuries. Writings about such topics as fossils, gems, earthquakes, and volcanoes date back to the early Greeks, more than 2,300 years ago, and perhaps even before. This is indeed valid as we had interacted in many ways with geology, perhaps from the beginning of human consciousness, and geological processes and products do clearly have an impact on all of us. In contrast, our modern civilization can also dramatically influence geological processes and products by different ways of intervention of natural resources in order to satisfy the supply chains. The most famous ancient Greek philosopher to refer to the earth was Aristotle. Aristotle was one of the first people to record any geological observations. He stated that geological change was too slow to be observed in one person's lifetime. However, his explanations about the natural world, including geological processes and products, were not based on keen observations and experiments. Instead, they were arbitrary pronouncements in an attempt to provide an explanation for his surrounding world. first. He believed that rocks were created under the influence of the stars and that earthquakes occurred when air crowded into the ground was heated by central fires and escaped explosively. For instance, when he observes a fossil fish, he stated that, quote, "A great many fossil fishes live in the earth motionless and are found when excavations are made." Aristotle's explanations prevailed due to his reputation and place held in society. They unfortunately continue to be viewed as authoritative for many centuries. This perhaps inhibiting the exploration of different ideas that could have perhaps provided alternative views to these natural occurrences. It was perhaps only after the Renaissance of the 1500s and the overall awakening in the observation and understanding of nature that more people became interested in finding answers to questions related to our planet beyond the religious scholarly realms. Following Aristotle, another Greek philosopher, Theophrastus, also made contributions to several fields in natural sciences, including geology, and was the author of Perilithon on stones. During the Roman period, Pliny the Elder wrote in detail of the many minerals and metals. His book, Natural History, compiles information gleaned from other ancient authors and became a model for later encyclopedias and scholarly works as a result of his breadth of subject matter, its referencing of original authors, and its indexing. Pliny the Elder extensively discusses metals and minerals, including crystallography, indirectly introduces mineral properties such as hardness, and gives a great deal of credit to his predecessor, Theophrastus. Abu al-Rayyan al-Biruni was one of the earliest Persian geologists whose works included the earliest writings on the geology of India, hypothesizing that the Indian subcontinent was once a sea. Drawing from Greek and Indian scientific literature that were not destroyed by the Muslim conquest, the Persian scholar Ibn Sina, also known as Avicenna, proposed detailed explanations for the formation of mountains, the origin of earthquakes, and other topics central to modern geology, which provided an essential foundation for the later development of geology as a science. In China, the polymath Shen Hu formulated a hypothesis for the processes of land formation. Based on his observations of fossil animal shells in a geological stratum in a mountain hundreds of miles from the ocean, he inferred that the land was formed by the erosion of mountains and by deposition of silt. He wrote extensively on a wide range of different subjects. His written work included 2 geographical atlases. Georgius Agricola is credited as the founder of geology as a scientific discipline, with the publication of his groundbreaking work and his greatest contribution to paleontology, De Natura Fossilium, in 1546, as well as the first book on physical geology, De Ortu et Causes Subterraneum, the same year, and with the publication of his celebrated De Re Metallica, that literally translated means On the Nature of Metals. In the mid-1600s, in an attempt perhaps to validate the Bible narrative dealing with the creation of the earth, in a world governed and driven by religious beliefs, the Anglican Archbishop James Ussher, Primate of all Ireland, published a major work that had immediate and profound influences. A respected scholar of the Bible, he published a reconstructed chronology of the Earth's history based on biblical interpretations taking into account the creation of humanity. In his influential publication, the Earth was created on October the 22nd, 4004 BC. Reverend Ussher wrote these famous Annals of the Old Testament, deducted from the first origins of the world, in which he arrived to that date during the latter period of his life. This monumental piece of work contains over 12,000 footnotes from secular sources and another 2,000 references from the Bible and the Apocrypha. This allocated a rather young age to the Earth by modern standards, particularly if we think that currently the preferred unit for measuring time in geology is the millions of years. Thus, because of his influential position, the understanding was that the Earth was only a few thousand years old. Reverend Ussher's work had a profound influence during the subsequent 17th and 18th centuries. Western thought about the Earth's features and processes was strongly influenced by Ussher's calculation, and is perhaps in part based on this understanding of how the features and processes of the Earth are formed that emerged a doctrine still prevalent today called Catastrophism. This guiding doctrine in earth science postulates that the Earth landscapes were the result of catastrophic events, sudden, short-lived, violent events likely with worldwide effects. Thus, the resulting modern landscape were shaped primarily by great catastrophists. Features such as deep valleys, mountain change, canyons, etc. were explained as having been produced by sudden and often worldwide disasters produced by unknowable causes that no longer operate. In a broader sense, it is indeed unavoidable to believe that this doctrine fit perfectly within a religious-dominated scholarly world, where the knowledge was mainly concentrated in the abyss and likely was an attempt to fit the rate of earth processes to the prevailing ideas about the age of the earth, laid by religious-affiliated scholars like Reverend Usher. Nicholas Steno is credited with the law of superposition, the principle of original horizontality, the principle of lateral continuity, and the principle of cross-cutting relationships, for defining principles of stratigraphy, as well as his pioneer work on the field of crystallography. William Smith drew some of the first geological maps and began the process of ordering strata by examining the fossils contained in them, thereby providing the basis of correlativity of strata and relative dating by using the fossil content of a particular bed. Smith's observations were largely done using Steno's superposition and lateral continuity of bed principles, thus allowing a systematic orderly arrangement of the fossil of sedimentary successions. In 1763, Mikhail Lomonosov publishes his treatise on the strata of the earth. His work was the first narrative of modern geology, based on the unity of processes in time and explanation of the earth's past from the present. Lomonosov, a Russian naturalist, is credited to be the author of the first systematic treatise in scientific geology, a significant contribution towards the birth of geology as a modern science. In the late 1800s, a Scottish physician and gentleman farmer named James Hutton published this amazing book, Theory of the Earth, in 1795. And it's in this book that Hutton presented a fundamental principle that is, until today, considered perhaps the fundamental building block of modern geology: uniformitarianism. This guiding doctrine states that the physical, chemical, and biological laws that operate today have also operated in the geological past. This means that the forces and processes that we observe presently shaping our planet have been at work for a very long time, perhaps not at the same rate and intensity, but they had and are still always acting, an ongoing sort of a background process that is still and always operating and governed by nature laws and principles. Thus, to understand ancient rocks, we must first understand present-day processes and the resulting products. This idea is commonly stated as the present is the key to the past, and like catastrophism, is still operating even within our short span of human life. Thus, there is an inherent idea behind Hutton's postulate, and it is the fact that the Earth is quite old. The notion that changes occur in large time spans could in principle be difficult to wrap our heads around, perhaps incomprehensible and in part imperceptible for humans due to the fact that we don't live that long to see it. However, at this point, it is important to say that when we state that the geological processes in the past were the same as those occurring today, it does not necessarily imply that they always had the same relevance or that they operated at precisely the same rate. Local conditions vary from region to region, and processes can be affected by conditions such as climate regime, tectonic setting, temperature, and composition of a particular rock. Thus, careful analysis of geological processes must be studied on a case-by-case scenario where context is important and will largely dictate the rates of change and final products. Due to the immense time spans we are dealing with, prior to Hutton's publications of the Theory of the Earth, no one had formally even grasped or effectively demonstrated that geological processes occur over extremely long periods of time. However, Hutton persuasively argued that forces that appear insignificant can over long spans of time produce effects that are just as great as those resulting from sudden catastrophic events. Thus, Hutton's idea was quite radical, and it is easy to conceive how a landscape changes due to a local, regional, or global event, because that occurs within the span of a time of a human life. But it is a bit more challenging to visualize how little by little, day by day, a landscape can change over the spans of hundreds of thousands to even millions of years. Back then, the followers of Hutton were called Plutonists because they believed that some rocks were formed by volcanism, thus formed by fire and after the deposition of lava from volcanoes, a theory originally proposed by the Abbé Antoine Moreau with reference to his studies of volcanic islands. However, an opposing theory to Plutonism was Neptunism, led by Abraham Werner, who believed that all rocks had settled out of a large oceans whose level gradually dropped over time, leading to the crystallization of minerals in the early Earth's oceans. The controversy lasted into the early years of the 19th century, but the works of Charles Lyell in the 1830s gradually won over support for the uniformitarian ideas of Hutton and the Plutonist. However, sedimentary rocks such as limestone are considered to have resulted from processes like those described by the Neptunist, so modern theory can be seen as a synthesis of the two approaches. And it was perhaps the challenging task that was to prove his ideas that led to Hutton to apply a thought process in the need to verify his hypothesis that he has formulated to explain his observations for gradual changes on the Earth through time. Unlike his predecessors, Hutton carefully cited verifiable observation to support his ideas, and this marks a significant point as it was in this frame of observations that helped him to test and formulated hypotheses that led to his interpretation of gradual change that provided a platform for geology as a science. In other words, in finding the evidence to defend his postulates, Hutton applied the scientific method, whereby, beginning by a set of observations, a hypothesis to explain them is formulated and then tested to be validated or discarded. If positively tested, that will ultimately lead to an interpretation to explain that particular object, phenomenon, or process under study. And it is in this context that arguably, to him, James Hutton, the birth of geology as a modern science is ascribed to. For instance, when Hutton argued that mountains are sculpted and ultimately destroyed by weathering and the work of running water, and that their wastes are carried to the oceans by processes that can be observed, Hutton said, quote, "We have a chain of facts which clearly demonstrates that the materials of the wasted mountains have traveled through the rivers." And further, quote, "There is no one step in all this progress that is not to be actually perceived." He then went on to summarize this thought by asking a question and immediately providing the answer, quote, "What more can we require? Nothing but time." Thus, in uniformitarianism, time always had and will continue to play a fundamental role. I think what I find the most fascinating about that reasoning we just reviewed is the fact that it gives us access to Hutton's mind, so we can see how a geoscientist thinks. The reason I'm saying that is that, to a larger extent, this reasoning remains virtually the same in many modern scientists. Today we realize more strongly than ever before that the present gives us insight into the past, and that the physical, chemical, and biological laws that govern geological processes today remain unchanging through time. So to see how everything started for geology as the vibrant, multidisciplinary integral field we recognize today is quite amazing, as we could witness how pioneers, giants of geology such as Hutton, reasoned to build the fundamental blocks onto which modern geology is supported. And he is considered a giant by installing the notion that at the time all the materials that compose the earth can be modified by all the different processes that act on it. Thus, it is important in the light of the scientific method to examine both the materials that compose our planet and all the processes that modify them. Using this approach, I hope you learn here in this channel dedicated to all these interesting aspects of geology that continue to intrigue us and inspire curiosity. Another major contributor to the development of the field of earth sciences and a major figure in natural sciences research in the early 19th century was the French naturalist Georges Cuvier. Cuvier is considered as one of the founding fathers of vertebrate paleontology, and he expanded Linnaean taxonomy by grouping classes into phyla and incorporating both fossils and living species into the classification. Cuvier is also known for establishing extinction as a fact. At the time, extinction was considered by many of Cuvier's contemporaries to be merely a controversial speculation. In his essay on the theory of the earth in 1813, Cuvier proposed that now extinct species had been wiped out by periodic catastrophic flooding events. In this way, Cuvier opposed uniformitarianism and became the most influential proponent of catastrophism in geology in the early 19th century. His study of the strata of the Paris Basin with Alexandre Brongniart established the basic principles of biostratigraphy. Following the publication of Hutton's ideas and the rise of uniformitarianism, another important figure was Sir Charles Lyell, who first published his famous book, Principles of Geology, in 1830. He presented to a wide public audience the idea that the Earth was shaped by the same natural processes still in operation today, operating at similar intensities. The combination of evidence and eloquence in Principles of Geology convinced a wide range of readers of the significance importance of deep time for understanding the Earth and environment. Lyell's scientific contributions, including a pioneering explanation of climate change, providing the explanations about earthquakes, and development the theory of gradual backed-up building of volcanoes. In stratigraphy, his division of the tertiary period into the Pliocene, Miocene, and Eocene was highly influential. His book, Principles of Geology and Friendship, influenced the thought of great figures of his time, such as Charles Darwin and Alfred Russel Wallace. Darwin, who successfully promoted the doctrine of uniformitarianism, held a long-term friendship with Lyell. However, as a science, the influence of geology on Darwin's work was huge. His early training at Edinburgh and Cambridge, and the lessons he taught himself on the Beagle, laid the foundations for a great career in geology. Darwin published successful theories on a range of different geological problems, from coral reefs to volcanoes, and from the fossil barnacles to fossil giant sloths. This work helped establish him as a scientist and earn him memberships to the great scientific societies of the day. Darwin's geology was also important in the development of his theories of evolution, teaching him important lessons in gradualism, taxonomy, classification, comparative anatomy, and acquainting him with the finer details of the fossil record, which he would use to support his ideas, and others would use to dismiss them. Modern geology embraces both catastrophism and uniformitarianism. Perhaps the best way to describe it is that punctuated catastrophic events take place against a backdrop of uniformitarian, timeless, continuous processes. For example, the meteorite impact, thought to be the main driver of the dinosaur extinction, took place as a single event, but before and after the impact, the slow, continuous, to say so, uniformitarian processes continue taking place independently, for example, of which species colonize a particular niche following the demise of the dinosaur era. Some of the most significant advances in geology throughout the 19th and 20th century have been the estimation and subsequent refinement of the methods to calculate the age of our planet, and the development of the theory of plate tectonics, a theory that arose from two separate geological observations, seafloor spreading and continental drift. Plate tectonics constitute a unifying theory that revolutionized earth sciences and raised up its importance to be the science as we know it today by providing a conceptual framework that allows the explanation of a multitude of processes that affect human life and habitat, such as earthquakes and volcanoes, among others. There is something that I particularly find really nice, and is the notion that geology is a science that takes place outside. Perhaps many of you watching this channel are of that perception too, that all related geology occurs outdoors. This is indeed still right to a certain extent. However, a lot of geology also involves work in the laboratory. This involves several analytical techniques that allow us to understand different aspects of the geological processes and their resulting products, like the scale of geological time, the composition of a particular mineral, or temperature of formation of a given rock, how landscapes evolve through time, etc. Both aspects, field work and lab analysis, deal with how geology takes place, and the techniques carried out to do the work conducive to the understanding of the Earth are still a perfect combination to derive amazing and inspiration from. Today, planet Earth is conceived in a more larger context, and our conception has broadened it way much more. We see our planet as being part of a much more larger planetary ecosystem, and this has inspired our curiosity to go beyond the Earth and explore other planets. From our ancestors' observations of the night skies to our modern space exploration, our planet and planetary system continue to be the source of admiration, wonder, and divinity. But we don't need to go that far to see how amazing our planet is and all its interlocking systems offer. There are still areas from our planet to understand, for curiosity and to draw inspiration from. More importantly, there are so many things to learn about and comprehend. I hope you enjoyed this first video and we continue learning about our planet. We will see each other soon. Well, thank you for watching up to this point. I hope this video contributes to increasing your admiration and amazement towards our planet. Please let me know in the comment box, what is that thing that you think is the most amazing about our planet? And more importantly, why? I like minerals, for example. I like their shapes, their colors. I also like the seasons. I like water and the oceans, but also volcanoes. Why? Well, because it shows that our planet is not a static entity, lifeless or stagnant. To the contrary, it is a dynamic system made of many parts that interact with each other. So yeah, I like that dynamic aspect from our planet. And you, please let me know in the comment box and I will do my best to answer all of them. Don't forget to like, share and subscribe, and I will see you in our next video. Ciao!